This is a video. I suppose it's a long time coming in a way, and the only reason I'm making it is due to well-known baller dishonesty, basically. Where there's a couple of things that they do when it comes to the elevation angles. They want to be okay with an elevation angle being a right angle triangle when you're taking an angular size measurement, something that can't exist in their paradigm. But they're not okay with it being a right angle triangle when you're measuring an angle to a celestial body. Now, the thing is their argument is, if it's a right angle triangle, then you'll be able to know the height of the star, right? Now, there's a couple of problems with that. Number one problem is they're pre-assuming that the star, or whichever celestial body, is a solid object that has a geometric location, right? I have two diagrams here. I'll just go into this one, right? This is it's not done, I don't have the actual angles in here. I've done it before, a lot of people have done it. I don't need to, I just need to show the depiction of it for this purpose. So if I was to do it with the angles involved as well, this line here would be higher in comparison to this one. But it doesn't matter because I don't have any heights because this is depicting a celestial body. Don't have any actual heights, so it don't matter. But for the purpose of this, what I want to show here, it doesn't matter if the angles aren't in here. I'm just depicting a line with a claimed angle to it. That's all. I don't need to do the whole thing out with all the angles because that doesn't make any difference. You just end up with this line here. That's all it does. Here I have unknowable altitude. Now, this is really important, right? Why that's really important is, if this is Polaris, right? And if I'm standing here and Polaris is 90 degrees directly above my head, I have no idea what height Polaris is. I have no way to measure between where I am and Polaris. Now, Polaris would have to be a solid object that has a geometric location, right, in the sky, for me to even consider measuring a height to it. I can't. There's no way for me to measure a height to it. Because if I go from here up to this height, whatever that is, then Polaris will go from here up to here, right? Because I'm just going to move this one up to here. So Polaris, this unknown altitude, if I raise my altitude from here to here, Polaris will appear to go from here up to here for me. So my point being is that I can never directly above me raise up and determine the height of Polaris. I can never do that. Nobody can. It's impossible. If I'm taking an angle, let's just say I'm taking an angle to Polaris and I'm 600 miles away from its GP, which is here, right? This is the GP point of Polaris in this diagram. Then, right, I will get an 80-degree angle, right? But this doesn't matter if I'm at sea level or 6 miles above the earth in an airplane. I will still, if I'm 600 miles away from what would be the GP point of Polaris, right? I am in an airplane. Once I make my horizontal, I will still get 80 degrees. So if I'll get an 80 degrees, right, with Polaris being in an apparent altitude here of 80 degrees from 600 miles away at sea level, and I'm getting the same 80 degrees 6 miles above sea level in an airplane, that means that as I rise, Polaris and all the other celestial bodies, all the stars, all appear to rise with me. So if I go up that much, Polaris goes with me. I go up that much, Polaris goes with me. Does it actually go with me? It only appears to do so. I don't know what Polaris is. I don't know what any of the celestial bodies are. But it appears to do so. right? But because of that, right, that's the second problem. How do you measure the altitude, the actual correct height of something off of sea level if that rises as you rise? That won't happen with a mountain or a tower or a building or whatever. As you rise up, the angle to the top of the mountain will be less from the horizontal you make, right? Just to show that, I'll show it now, right? Right, here is mountain height, right? And here I have an angle to the top of the mountain. If I raise up to this, up halfway here, my angle to the top of the mountain will be less. I won't get the same angle, but that doesn't happen with the celestial bodies. As I raise up, the celestial body appears to rise with me. But that won't happen with the mountain. So if I come halfway up the height of the mountain and take an angle here, then I will get an angle between this point and this point, because the top of the mountain is not going to appear to rise as I rise. That doesn't happen, right? That will never happen. Whereas with a celestial body, it does happen, right? So you can't get a height to a celestial body. Regardless of how many triangles you have, you can't get a height to a celestial body. It can't be done, right? Because the celestial bodies do not adhere to terrestrial geometry. Now, the lawyers and the dishonest types on our opposing side want to use this ridiculous straw man, and they keep doing it, which shows that they've got nothing. You can't have anything if you keep on having to go back to some dishonest straw man that you know is not correct. Like, they're aware of this. They can ask anyone who has navigated with a sextant, and they will be told that yes, the star appears to rise as you rise. That's why you can use a sextant with the sea horizon. You can use it with an artificial horizon on the top of a mountain, and you can use it with an aeronautical horizon in an airplane. And if you're over the same spot, or let's just say you're looking at Polaris in all those three instances, and you're at 45 degrees latitude at sea level, and if the mountain that you're at, that the other person is at with the artificial horizon, is also over the 45th degree latitude, and the person in the airplane with the sextant is also over the 45th degree latitude, then from their angles will also be 45 degrees. Even though those three people, the person at sea level, the person on the mountain, and the person in the airplane, are at three completely different altitudes. Right? Different elevations above the earth. Yet they'll all get 45 degrees. That doesn't happen with a mountain or a building or anything terrestrial. It just doesn't happen. Now, if we go back in here a second, every one of these here, let's just use the 600 one, right? There is a straight line between this point here and the GP point of Polaris. There is a line here that goes up to the 80 degree mark and a line back down to the 600. Now, that is the adjacent, this is the opposite, and that is the hypotenuse, right? It wouldn't matter if I do this out with the 10 degrees, that'll only move the 80 degrees up, right? I'll only make that line here bigger, right? I've done it before 2 or 3 times, and other people have done it. That's what the outcome is of the graph when you do it that way. The point being is that 80 degrees is an apparent height, right? So I can, right, take this 600 miles and this 10 degrees and work out an apparent height to Polaris, right, for this 80 degrees. I can do that, right, using trigonometry, right? But that would not give me, that's of no use to me because I don't know its actual height. I don't know its actual height to determine. So I can't determine this 600 mile distance from the GP of Polaris if I don't know Polaris's actual height. And Polaris doesn't seem to have an actual height because it appears to rise as you rise and lower as you lower. No matter what you do, Polaris and all the other celestial bodies, they do not adhere to terrestrial geometry. So consequently, I cannot use trigonometry and get a height to Polaris or any other celestial body because they're not like a mountain. This is for the borders. The top Polaris is not like the top of a mountain. They're not the same thing. Within your idiot paradigm, Polaris is a physical solid object. Sorry, Polaris is a solid object or whatever, made of, maybe it's not a solid, maybe it's made of plasma, whatever it is nonsense you're claiming. Right? The point is that it has a composition, it has a size, and it has a distance. Now, you never use any of those distances in celestial navigation because it shows that because the Earth's not a globe and it can't be used. But the point is that within your globe paradigm, right, it has a distance, right, from the surface of your globe, blah, 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 right? In reality, it doesn't those sizes and distances and compositions to Polaris mean absolutely nothing. No, there is no composition to Polaris. Nobody has the composition of Polaris. Nobody knows what it is. Nobody knows at what distances it is, if you could even say it has a distance. And nobody knows what size it is. All people know is it's the light in the sky that appears to rise as you rise and appears to lower as you lower. That's just the way it is. Well, when I say lower, I mean if you're in an airplane and you come down to sea level and you take the same angle, you take an angle over the same spot, you'll get the same angle. So Polaris would have to have appeared to lower as you lowered. Or if you go up from sea level to an airplane and take an angle to Polaris over the same spot on Earth over the same GP point, you will get the same angle. So Polaris appears like the rest of the celestial bodies, they appear to rise as you rise. Simple as. So you cannot, in any way, shape or form, it is impossible to gain an altitude to it. An actual correct height in feet, meters, blah, blah, blah. Because that's why in celestial navigation, they treat Polaris and all the rest of the celestial bodies as being at an infinite distance, which is nonsense because infinite doesn't exist in mathematics, right? But just the only way they can address it. They can't address Polaris and the rest of the celestial bodies in any other way because they don't adhere to terrestrial geometry. That's why they don't use trigonometry. Yet, to measure the elevation angle to Polaris off of your horizontal, whether it's your horizontal is at sea level or from the top of a mountain or from an airplane, you must use an elevation angle. And that means you're measuring off of this line here, right, vertically up this line. And this is this other line here. I'll just make that blue for a second. This other line here at the 600 mark. Sorry, I'll make it a bit brighter. This line here is your hypotenuse. So you have an adjacent here between 600 and the GP. You have the opposite, which is the thing that you're measuring, because you're measuring from the horizontal up the vertical to the point that where Polaris or whatever celestial body appears to be. And then you have your hypotenuse, which is from your position up to Polaris. So you're still measuring using a right angle triangle. Now, your process, because you don't know the height of Polaris and you can't find it out, your process of determining the distance from its GP cannot be gained. The process is not the use of trigonometry. You don't use trigonometry to find out that distance. And that leads me to the main purpose of the video. The angle, right, when it comes to an elevation angle to the celestial bodies, the distance, right, gives you the angle, right? So when you travel 600 miles away from the GP point of Polaris, that gives you an 80-degree angle. The distance will give you the angle, right? If you travel 1,200 miles away from the GP point of Polaris, that'll give you a 70-degree angle. And 1,800 miles away from the GP point of Polaris, this is nautical miles, that'll give you a 60-degree angle, right? The point being is that when it comes to an elevation angle with the celestial body, it's still a right angle triangle. You're just not using trigonometry to gain the distance. or to gain, you're not using trigonometry to gain the distance. It's the distance gives you the angle, as opposed to the angle giving you the distance. So after you've traveled a certain distance from the GP point of Polaris, or if a star has moved a certain distance from you, that distance determines the angle. Whereas it's, because we don't know, as I said, for about the 9 millionth time, the height of the celestial bodies. We don't, how can you even give them a height if they appear to rise as you rise? You can't. So it doesn't work. With the usual trigonometry doesn't work. Now you can do it, when I say it doesn't work, you can do it and gain an apparent height from 600 miles away for this 80-degree angle, and you can give this a height in feet and meters. But will it be the height of Polaris? Will it be any good to you? No, because you don't know what height Polaris is when it's at its 90 above your head, when it's at 90 degrees above your head. You need to know what height that would be at 90 degrees above your head. But how are you going to know that if you raise up 6 miles into the air, it appears to rise up with you? How are you going to know if you're in this position, whether at sea level on a mountain, or over this position, at sea level on a mountain, or in an airplane, you're getting the same exact angle, because it's appearing to rise as you rise. It's impossible to know the height of the celestial bodies. Technically, they don't have a height. So how could I use trigonometry to gain a height to something when I don't have the actual height? You cannot know the size of something if you don't know or the height of something. If you don't know, if you don't know its actual height, you can't use it to gain a distance from it. You need the height to gain the distance, and the distance to gain a height with trigonometry. You need to know one or the other. Now, when it comes to celestial navigation, we don't know the height of the celestial body, so we can't use an angle to it to give us a distance. What we can do is gain an angle, right, via the distance, so when we travel a certain distance from it, we will get an angle. So if let's say, travel from the GP point 600 miles away, GP point of Polaris 600 miles away, and I'll get an angle of 80 degrees, right? Then I subtract that angle from, I won't know, let's just say it's 600 miles straight off, but I'll find out it's 600 miles by subtracting that angle from 90, subtracting the angle from 90, it gives me 10, so my zenith angle is 10, right? 10 by 60 gives me 600, right? That's the way it works, right? So I'll know then that I have a 600 mile distance from its GP point. But what actually gave me the angle was the distance from its GP point, right? I didn't work out I didn't work it out with trigonometry, because it can't be worked out with trigonometry, because you can't know the height of it or figure out the height of a celestial body. You can only figure out your distance from its GP. That's it. But to do that, you were using a right angle triangle, because if you're claiming that we're not using an opposite, and this is not being measured, then essentially, right, what you're claiming is you're not measuring an angle at all. You're not measuring any elevation, because to measure elevation means to measure along the opposite. That's it. You're measuring along the opposite to gain a hypotenuse length and an adjacent. So you're measuring off of the adjacent along the opposite. That's what you're doing. That's how elevation works. It's the vertical height above the horizontal plane. Now, those two things don't exist. They can't exist geometrically on a globe, horizontals or verticals. But that's what happens in reality. It's not our fault, not my fault that your globe is wrong. It just is. You don't have those things on a globe because they can't work on a globe, because they're constant orientations. You don't have them. You can create a 90 degrees off of a tangent, but that's of absolutely no use to you, because it's not a constant position, constant orientation. It's continually changing. It's of no use. It's pointless. You don't have vertical, don't have horizontal. End of story. But when it comes to, right, when it comes to something we do know the height of, right, in the real world, right, like a mountain, like this mountain here, right, let's make it a bit smaller, right, if I know I'm taking an angle, right, to the top of this mountain, and I know the top of this mountain from this point here is 14,220 feet. Now it doesn't matter if if where I am is above sea level and the mountain is above sea level. It doesn't matter, or if I'm halfway up the mountain and I'm only measure. If I know that from where I am, right, to the top of that mountain, right, is 14,220 feet. And that means when I take an angle of 2.7263 degrees here, right? Sorry, not that one. Wrong one. Right. So I know the height of the mountain is 14,220 feet. I want to gain my distance to the mountain, so I put in 2.72 degrees. I didn't know the 6.3 or whatever, it doesn't matter for this purpose. So I put in 2.72 degrees, and that gives me a length of B, which is an adjacent length of 299,313.90933 feet. Right? So I want to know what that is in miles. So I turn it into miles, and it turns out to be 56.688 whatever miles. So let's say 56.7 miles almost, right? So I know, because I know the height of that mountain, the actual height, I can use trigonometry, right? I can use trigonometry to gain the height, to gain my distance from it, because I know the actual height. So I can gain a distance because of that. I can't do that with a celestial body, because I don't know the height of the celestial body, and it cannot be obtained. And you can't obtain the height of it because it appears to rise as you rise and lower as you lower. Like with the horizon appears to to move further from you as you rise and come closer to you as you go down. So how can you measure a distance to it? It's impossible. But it also moves around with the weather, and it'll change with optics. So you can't measure a distance to the horizon. You can never know the distance because it's always just only apparent. It's only an apparent distance. It doesn't have an actual distance. The same as the celestial bodies don't have an actual height. So if I can't measure an actual height and know the actual height of a celestial body, how can I use trigonometry to gain a distance from its GP point? I can't. But to use the GP point and to navigate using the celestial body, I must, right, use a right angle triangle if I'm going to measure the angle to it. Because there's always going to be, if this is a celestial body here, there's always going to be, just like with this mountain, a right angle where the vertical meets the horizontal, right? And I'm measuring off of the horizontal up vertically to the point where I see Polaris, like just up here, right? I may as well go up to this one, sorry. Right, so I'm measuring, right, off of the horizontal up vertically, right, from this point to where I see Polaris. And that tells me that I have an 80-degree angle. And from that 80-degree angle, I can then use the other function, right, to gain my distance from its GP. But the point is that the distance will give me the angle. Whereas in this scenario, right, the angle can give me the distance, right? Because I know the height of the mountain. So the angle can give me the distance. Whereas technically what's happening up here is the distance is giving you the angle. Because you can never know the height. Right? But that doesn't mean you're not using a right angle triangle. In both instances, you're using a right angle triangle. There is no if, buts, or maybes about that. That is a right angle. Right? That is directly connected to this via the same horizontal adjacent. There is no if, buts, or maybes about that. That's what's happening. So when ballers come at us with this stupid straw man about give me the height of Polaris above your flat Earth with using trigonometry, it's like if you're saying you're using a right angle triangle, they know that they're lying. They know that all they're trying to do is avoid the reality of the situation. They know that they don't know the composition of Polaris. They know they don't know what size and distance Polaris is. They know this, but they're willing to lie. They're willing to be completely dishonest, right? And now I don't know why they're even referencing angles in the first place, but they are, right? But they know that what they're asking us to do can't be done, not by us, by anyone. It can't be done. Nobody knows the height of Polaris. It can't be known. Yet they want to use that straw man. But either way, right, in both instances, you will be using a right angle triangle, you will be using a flat earth, right, whether this is at sea level or it'll either be at sea level or parallel to sea level at all times, right? At all times, that will be the situation. So let me just come in here a second. So let's just say, right, let's see, right, let's just say that, oh, sorry, I'm going to get this segment here. Let's just say that, one second now. Sorry. Now, let's just say that this line here, right, is sea level, this blue line, right? And this is my height above sea level, right? And this is the height of the mountain from my height above sea level, right? So the mountain is more than 14,220 feet. The mountain is, let's just say, whatever extra amount that is. Let's say an extra couple of thousand feet, whatever, right? I know that I can measure, right? If I subtract I know for certain that if I subtract my elevation from the full elevation of the mountain, of which I do know, right, in feet and meters, that I can then take an angle, right, know that the rest of the rest of the mountain from my elevation up is 14,220 feet. I can then determine that I'm 56 miles away, over 56 miles away from that mountain in a straight line, using a right angle triangle, right? I can then determine that, right? There is no if, buts, or maybes with that. And that means that the baseline of my right angle triangle must be parallel to sea level. There is no if, buts, or maybes about that. And at the GP point, I'm just going to get a point here. Sorry, now. All right, so let's just say that's the GP point of the mountain, right? Make it, right? That here is the GP point at the mountain, right? Let's just say, sorry, I make it green. That's the GP point at the mountain. And this is my GP point, right? Directly below me. And the both of them are on sea level, right? The only way that this can work, right, and I've gone through this in the past, the only way that this process can work is if the earth is flat. My adjacent of my right angle triangle, right, that I'm using to measure the angular size which would be a perspective size, something that doesn't exist in heliocentrism. End of story. It doesn't exist in the globe maths. There is no angular size or perspective change in the globe maths, right? That doesn't exist. So straight away, once you're measuring the angular size of something, especially let's say a mountain at a distance, then straight away the globe is over. There is no if, buts, or maybes. The globe is over. And if you're breathing air, that means there is no globe either, right? The fact that this proves, right, my adjacent here, right, has to be a straight line, and I know that whatever angle I get here, right, if I know the actual height of the rest of the mountain, that angle will give me a correct distance to the mountain. That is true in all instances, right? There is no if, buts, nor maybes about that. And the only way that works is that if mean sea level, right, level is two-dimensional, not three-dimensional, is not three-dimensional, right? Because level can't be three-dimensional. Mean sea level has to be horizontal, and my adjacent has to be parallel with mean sea level. That means that mean sea level that runs which is an average of high and low tides throughout the world, right? That mean sea level is a straight horizontal line. That's the only way it works. It can't work any other way. And it also means that that the zenith, right, the mountain's zenith and my zenith have to be parallel, right? There's no way around that. And the line from here, which is halfway up the mountain, down to the GP point, and the line from where I am down to my GP point have to be parallel. So you're using parallel verticals and parallel horizontals. We know this works all the time, forever. It never doesn't work. It always works. We know this. We use it all the time. And the fact that it works means the earth is flat. That's it. There's no if, buts, no maybes, no way out of it. Right? The earth is flat. That proves it outright. There is no going against this. You can't beat it. Because on a globe, you will not get that angle to match the distance. It can't happen. If you even had, hypothetically, if you even had angular size, which you don't. But hypothetically, if you had angular size, it would make no difference, because the angular size you get right here, because there'll be a lean between these two, my zenith and the zenith of the mountain will be leaning away from each other, as I've shown in previous videos. Right, that means you won't get the angle you're getting here. Then the angle you do get will not give you the distance. It'll be wrong. The whole thing will fail. But it doesn't fail in reality because the earth is flat. Now, before I finish, I just want to go back up here very quickly. I cannot take an angle, elevation angle, to the apparent height of any celestial body without measuring along the opposite. An elevation angle is an elevation angle. How you use it afterwards to gain whatever you want to gain, right, has nothing got to do with whether that elevation angle is a right angle triangle or not. All elevation angles are right angle triangles. There's always a right angle at the base of the mountain, or wherever it is that whatever it is that you're measuring the angular size of, and there always is a right angle triangle a right angle at the GP point, or at the base of your elevation angle to the celestial body. And it doesn't matter if you're in an airplane and this is 600 miles, and let's just say down here is sea level. The point is that this right angle here will be directly either on or directly above the GP point, depending on your elevation and altitude. But it will always be a right angle triangle. You cannot measure an elevation angle without measuring the opposite. That's what you're measuring. Right? Any of these people, if they want to claim you're not measuring a right angle triangle, then they're claiming you're not measuring the opposite, which means you're not measuring anything. Because you can't measure from here up to here without measuring it vertically. Are these people thinking that you're measuring in an arc? Is that what they're thinking? That you have an arc going from here to here? You don't measure in an arc, right? You measure in a straight line, a vertical. So no matter whether it is with a celestial body or a mountain or anything else, right, that you're measuring an elevation angle to, you're always using a right angle triangle. How you determine afterwards your distance from it or anything else, right, determines on the information, is purely dependent on the information you have concerning that thing. So if I have the information of the height of a mountain, right, I can determine my distance from it. If I don't have that information concerning a celestial body, then I can't use that same process to determine my distance from its GP point. Right? I can do that with a mountain or a tower or a building, but I can't do it with a celestial body. But I still must use an elevation angle, which is a right angle triangle. So it's my process after I've measured that right angle triangle. The process I use after that is determined by the object. Right? It's that simple. So please, can we stop this ridiculous, dishonest straw man that ballers, is completely fraudulent. You know this. Right? We shouldn't have to say this to you. I shouldn't have to make this ridiculous video. I shouldn't have to do that, but I have to, because you people cannot stop being dishonest. You cannot measure the elevation of something without using a right angle triangle. Can't be done. Okay, I'm going to leave it at that. Thanks for watching.